So I want to talk about looking at classifiers, and in particular, how do I look at this VMM winner-take-all classifier structure? And in particular, kind of what is the theoretical structure underneath this? Now you may have seen from other lectures and other discussions that a VMM winner-take-all is a universal approximator. And you go, great! Now how do I work with it? I mean, that's fundamentally what you'd have to deal with. So then the question is, okay, what kind of insights can I pull from like maybe other networks or other learning things that also help me bring that intuition across here? And what are sort of fundamental properties of these networks that allow me to get intuition of this? So instead of like doing pages of math, I thought I'd do sort of pictures, which basically do the same sort of equivalent mathematical derivation for you, and you can kind of see the steps. But the main part of this is it allows you to go, here is sort of the basic computations we have. And I want to be thinking about, what might transform into a typical vector matrix multiplication, input times a set of basically weight vectors, right? A whole sequence of them creates a whole set of metrics that goes into a k-winner-take-all network, and we'll look at different pieces of that to go to an output. All right, so then the question is what kind of transformations are, and what is the big thing that we're going to need to look at this? And the big aspect is the fact that a winner-take-all network is effectively a generalization of doing differential pairs. And what is the biggest thing you get out of a differential pair from a circuit is a common mode rejection. So we think of common mode rejection as rejecting the common mode between two inputs. What is common between two signals, right? Well, could I reject what is common in 3 signals, or 4, or 5? Okay, or n, where n scales to a larger amount. That is at the core of what's going on here. And so what you realize is that anything that is in common between between all of these various inputs here, all these various metrics you might say that you're computing, well, it's as if it's not there. It doesn't matter, right? And so fundamentally, that property is something we can go through with all of this mathematics and all of these different things. So for example, imagine I take a whole set of input. I have an inputs going into this, and I take my weight vectors, which are now vectors W1, 2 through M, and I apply a weight vector to it, W0 to all of those. They could be all the same values in that vector. They could actually be different, actually, which is kind of an interesting property to think about. And I have this input times, well, I know this isn't a linear operation, so it goes against all of these W's, right? But that input times all of these W0s is the same value. So that means it's going to just add an offset to each of these inputs. And you think to yourself, that doesn't matter anymore. So I would just eliminate it. So that means this network is identical to this network. And you'd say, that's a very nice example, but why would I care? Here's an interesting question experimentally. I could now say, here's my weight vector, and I could multiply it against, theoretically, another weight variable that just scales it up. So it might be more difficult to have negative weights, but by scaling something up, it's the same thing. So I can always have a constant weight offset. So if I come over here, it allows me to get negative weights without having to actually implement the additional hardware that often requires to do that. Oh, wait a minute, that's already significant. The second part is this. So now I go, imagine now I actually scale these. Well, if I scale them by some amount, all I've done is I've simply scaled the metrics coming into this. And after that, I'm going to do a comparison operation. So assuming that there's sufficient gain in this, there's no difference because Well, I scale it plus there's an offset. Well, the offset I already know I get rid of, so that's already one property that's gone. That helps me. So then I just scale it. Well, the scaling gives me the same thing all over again. So I can renormalize wherever needed, and it all just works. That's kind of useful too, because you might say, well, maybe I need some more range somewhere. Well, if things just rescale, I'm good to go. So you think, wait a minute, this actually now gives me a lot of different possibilities. So now eventually I might extend this kind of model to one thing further. Imagine I have an input with then a set of offsets. And it's not uncommon to do a weight set plus an offset elements to work with. Many different classifier networks do this. This is not unusual. So, and actually it's very easy to implement. It's just simply a constant input going into, say, a floating gate element or something of that sort. Very easy to do, not really asking much. Okay, but what does that do? Well, here's another case. Imagine I have a constant input offset going across all these weights. Well, you can kind of show that this is equivalent to having a whole bunch of inputs plus all those weights, that constant that I added to it. Again, things are linear, no problem, right? Right, so at that point, that looks exactly like this structure. Why would I care about that? Well, the reason I care there is that now this is a constant input offsets means I don't need to create negative inputs, so effectively I have them even if it's positive. So effectively, I can, from a hardware standpoint, get away with one quadrant multiplication, and this just works. By the way, most of the techniques that we often use in other hardware approaches to get one quadrant multiplication in other kinds of classifier networks effectively go through the same thing. You're effectively creating one level or another the same sort of common mode rejection in your structure. And this is a longer discussion, but it's something that you see, and it's something of the beauty of sort of the winner-take-all networks and how you generalize it. But here's what gets much more fun beyond that. As if that's not cool enough from a hardware standpoint, because anytime you go from 4 quadrant to 1 quadrant, you simplify things, that's a huge amount that you can get done. But think for a moment further. What else could happen? Well, here is an interesting one. You get equivalences with self-organizing maps and vector quantization. Now, these are algorithms we know something about. We know their learning patterns. We know how to build them. We know a whole bunch of things of their various learning properties. Well, it turns out there's ways to show equivalences. And one of the interesting ones is, say, well, Euclidean distance metrics, which is usually the heart behind both of those structures. You could say, well, if I had an input and then I computed those and then went through a winner-take-all network, this is sort of typically what you would do for building them. Here's an interesting thing. Because of the quadratic multiplication of x squared on the front, it's the same for all of these. Guess what? The common mode rejection says, bye-bye. It's gone. It doesn't matter. This is huge. Because now what am I left with? Multiplication of input times a whole bunch of weight matrices, and I have some offsets. Oh, that's cool, because that means that looks like this. And yes, it's a universal approximator. We shouldn't be shocked. But the insight and the intuition is huge, because we know how these things work. And so there's no reason, by the way, to build those models, because this is clearly going to be a simpler approach. Because to do all the quadratic multiplication and stuff is just more complicated math, more complicated stuff in the circuitry itself. And this simplifies. Well, here's something else that gets fun. If I have, because of the gain property, I can extend this now and say, well, if I have nonlinear functions here that are monotonic, like an exponential, now I can then, turns out that monotonic function disappears. This is actually very important when you start to ask a number of different algorithms, one of which being when you look at coincidence detection in dendrites and you look at that modeling structure. This is actually very fundamental and actually was the original way to think about this structure. But I can now talk about exponential. So now think about it. Something quadratic going into something exponential that's monotonic. This opens up all the Gaussian mixture models, particularly when you start talking about putting nulls into the structure. Areas that kind of then push away areas where you can actually separate out the space. And this gives you a way to talk about how do you think about implementing Gaussian mixture models in the structure. And I imagine that there's a number of other different approaches, and this starts to get the imagination rolling. But imagine what can be done and the way you think about it. Why is it important? Well, it says, hey, if I have a network that already works, how do I transform it? But two, if I have a network that works, if I have a way I want to train a network given a data set, I can start building training algorithms. In fact, this is exactly how these training algorithms originally got developed, was to look at structures like this and go, I see all the equivalences, how do I now build this in an effective way to start building powerful training algorithms?